Figure 1. The red crystals above are called rhodochrosite. Most of the best specimens of this striking gemstone, including the one in the photo, have been found in central Colorado. What are the properties of crystals? How are the atoms or ions that make up crystals arranged? What is responsible for the beautiful colors of minerals and gems? This chapter will reveal the answers to these questions, as you learn about the composition and properties of ionic compounds and of pure metals. In an ionic crystalline solid, positive and negative ions are arranged in an orderly, repeating fashion. The colors are contributed by various amounts of transition metal ions in the crystals. The red color of rhodochrosite comes from manganese, carbonate, MnCO3. Metals also have a crystalline structure, which contribute to the familiar properties of metals like malleability and electrical conductivity. We begin with a detailed look at how ions form. John W. Schultz, Flickr Grunman. www.flickr.com/photos/Grunman/55591150994. CC by 2.0. Chapter Outline. 8.1 Ions. Lesson Objectives. Be able to determine the number of valence electrons for any element and draw an electron dot diagram for any atom. Use the octet rule to predict the charges of the most common ions formed by the representative elements. Write electron configurations for ions. Identify other atoms or ions that are isoelectronic with a particular ion. Know that transition metal ions with either half-filled or completely filled d sublevels are particularly stable. Lesson Vocabulary. Electron dot diagram. Isoelectronic. Octet rule. Check your understanding. Recalling prior knowledge. What is the Aufbau principle? What is the name of the energy required to remove an electron from a neutral atom? How does the energy required to remove the first electron from an atom compare to the energy necessary to remove subsequent electrons? As you learned in previous chapters, ions are formed when atoms lose or gain electrons. Metal atoms have relatively few valence electrons, so when neutral metals undergo chemical reactions, they tend to lose those valence electrons. Nonmetals have more valence electrons than metals, so when nonmetals undergo reactions with metals, they tend to gain electrons. In this lesson, we take a closer look at ions and the physical and chemical properties of ionic compounds. Electron dot diagrams. Recall that the valence electrons of an atom are the electrons that reside in the highest occupied principal energy level. Valence electrons are primarily responsible for the chemical properties of various elements. The number of valence electrons can be easily determined from the electron configuration. Several examples from the second period are shown below, table below. Note that for each of the second period elements, the valence electrons are in the second principal energy level. Element. Electron configuration. Number of valence electrons. Lithium. 1s22s1. 1. Beryllium. 1s22s2. 2. Nitrogen. 1s22s22p3. 5. Neon. 1s22s22p6. 8. For elements in the S and P blocks, the number of valence electrons can easily be determined from the group number. In the S block, group 1 elements have 1 valence electron, while group 2 elements have 2 valence electrons. In the P block, the number of valence electrons is equal to the group number minus 10. Group 13 elements have 3 valence electrons, group 14 elements have 4, and so on. The noble gases in group 18 have 8 valence electrons, and the full outer S and P sublevels are what give these elements their special stability. When examining chemical bonding, it is necessary to keep track of the valence electrons on each atom. An electron dot diagram shows the valence electrons of an atom as dots distributed around the element's symbol. For example, a beryllium atom, which has 2 valence electrons, would have the electron dot diagram below. Figure 1. Since electrons repel each other, the dots for a given atom are distributed evenly around the symbol before they are paired. The table below, shows the electron dot diagrams for the entire second period. Group number. Electron dot diagram. 1. Figure 2. 2. Figure 3. 13. Figure 4. 14. Figure 5. 15. Figure 6. 16. Figure 7. 17. Figure 8. 18. Figure 9. Electron dot diagrams for all elements in a given group of representative elements are identical, except for the elemental symbol, because each element in one of those groups has the same number of valence electrons. Most transition metals have 2 valence electrons in their ground state, though some of the elements with unusual electron configurations have only 1. Go to http://hyperphysics.phy-astr.gsu.edu/hbase/pertib/perl-wis.html to answer the following question. From this periodic table, explain how valence electrons are added to the symbol from one column to the next. The octet rule. The noble gases are unreactive because of their electron configurations. American chemist Gilbert Lewis, 1875–1946, used this observation to explain the types of ions and molecules that are formed by other elements. He called his explanation the octet rule. The octet rule states that elements tend to form compounds in ways that give each atom 8 valence electrons. An exception to this rule is the elements in the first period, which are particularly stable when they have 2 valence electrons. A broader statement that encompasses both the octet rule and this exception is that atoms react in order to achieve the same valence electron configuration as that of a noble gas. Most noble gases have 8 valence electrons, but because the first principal energy level can hold a maximum of 2 electrons, the first noble gas, helium, needs only 2 valence electrons to fill its outermost energy level. As a result, the nearby elements hydrogen, lithium, and beryllium tend to form stable compounds by achieving a total of 2 valence electrons. There are 2 ways in which atoms can satisfy the octet rule. One way is by sharing their valence electrons with other atoms, which will be covered in the next chapter, covalent bonding. The second way is by transferring valence electrons from one atom to another. Atoms of metallic elements tend to lose all of their valence electrons, which leaves them with an octet from the next lowest principal energy level. Atoms of nonmetallic elements tend to gain electrons in order to fill their outermost principal energy level with an octet. Cations. As you have seen before, cations are the positive ions formed when an atom loses one or more electrons. The cations most commonly formed by the representative elements are those that involve the loss of all valence electrons. Consider the alkali metal, sodium, Na. It has 1 valence electron in the third principal energy level. Upon losing that electron, the sodium ion now has an octet of electrons from the second principal energy level. The equation below illustrates this process. The electron configuration of the sodium ion is now the same as that of the noble gas, neon. The term isoelectronic is used to describe 2 atoms or ions that have the same electron configuration. The sodium ion is isoelectronic with the neon atom. Consider the analogous processes for magnesium and aluminum. Both of these atoms form ions by losing all of their valence electrons, 2 in the case of magnesium, and 3 in the case of aluminum. The same noble gas configuration is achieved by all of these ions. In other words, the Mg2+ ion, the Al3+ ion, the Na ion, and the Ne atom are all isoelectronic. Under typical conditions, the representative elements form cations by losing a maximum of 3 electrons. We can also show the loss of valence electron, S, with an electron dot diagram. Na++E. Anions. Anions are the negative ions formed by gaining 1 or more electrons. When nonmetal atoms gain electrons, they often do so until they reach an octet of valence electrons in their outermost principal energy level. This process is illustrated below for the elements fluorine, oxygen, and nitrogen. All of these anions are isoelectronic with each other and with neon. They are also isoelectronic with the three cations from the previous section. Under typical conditions, a maximum of 3 electrons will be gained during the formation of anions. Outer electron configurations are constant within a group, so this pattern of ion formation repeats itself for periods 3, 4, and so on, figure below. Figure 10. It is important not to misinterpret the concept of being isoelectronic. A sodium ion is very different from a neon atom, figure below, because their nuclei contain different numbers of protons. One is an essential ion that is a part of table salt, while the other is an unreactive gas that makes up a very small part of the atmosphere. Likewise, sodium ions are very different than magnesium ions, fluoride ions, and all the other members of this isoelectronic series, N3, O2, F, Ne, Na+, Mg2+, Al3+. Figure 11. Neon atoms and sodium ions are isoelectronic. Neon is a colorless and unreactive gas that glows a distinctive red-orange color in a gas discharge tube. Sodium ions are most commonly found in crystals of sodium chloride, which is the chemical name for ordinary table salt. You can go to http://www.visionlearning.com/en/library/chemistry/1/atomic-theory-i/50 and http://www.visionlearning.com/en/library/chemistry/1/atomic-theory-2/51 to see animations of atoms and ions. Learning the octet rule can be fun. Watch this music video about the octet rule, http://www.youtube.com/watch?mark v=wzwk-mx_14e, 630. 1. How does this song compare an outer energy level with 8 electrons to emotions? 2. What are the 2 exceptions to the octet rule in this song? Transition metal ions. Transition metals belong to the d block, meaning that the d sublevel of electrons is in the process of being filled with up to 10 electrons. Many transition metals cannot lose enough electrons to attain a noble gas electron configuration. Additionally, you have learned that the majority of transition metals are capable of adopting ions with different charges. Iron, which can form either Fe2+ or Fe3+ ions, loses electrons, as shown below. According to the Aufbau process, the electrons fill the 4s sublevel before beginning to fill the 3d sublevel. However, the outermost s electrons are always the first to be removed when forming transition metal cations. Because most transition metals have 2 valence electrons, a charge of 2+ is very common for transition metal ions, as we have already seen in the case of iron. A half-filled d sublevel, d5, is also particularly stable. This type of configuration is obtained when an iron atom loses a third electron. Figure 12. A. Iron, 3, oxide, Fe2O3, is the primary component of rust. B. Iron, 2, sulfate, FeSO4, has been known since ancient times as green vitriol and was used for centuries in the manufacture of inks. Some transition metals that have relatively few d electrons, such as scandium, may be able to attain a noble gas electron configuration. Others may attain configurations that include a full d sublevel, such as zinc and copper. The resulting configuration above, with 18 electrons in the outermost principal energy level, is referred to as a pseudo-noble gas electron configuration. It gives particular stability to the Zn2+ and Cu and ions. Lesson summary. An electron dot diagram shows the chemical symbol of an element with dots that represent valence electrons evenly distributed around the symbol. The octet rule states that elements form chemical compounds so that each atom will acquire the electron configuration of a noble gas. Most noble gases have 8 valence electrons, except for helium, which has only 2. Representative metals generally lose all of their valence electrons when forming ions, leaving them with a complete octet of electrons from the next lowest energy level. Most nonmetals gain electrons when forming ions until their outer energy level has acquired an octet. Atoms and ions that have the same electron configuration are called isoelectronic. Common ions of representative elements are isoelectronic with a noble gas. When forming ions, transition metals lose their valence s sublevel electrons before they lose their d sublevel electrons. Half-filled or completely filled d sublevels give transition metal ions greater stability. Lesson review questions. Reviewing concepts. What is the maximum number of valence electrons that an atom can have? State the number of protons and electrons in each of the following ions: K+, F, P3, Ti4+, Cd2+, Cr3+. What is wrong with this statement? When a chlorine atom gains an electron, it becomes an argon atom. Why can the majority of transition metals form 2+ ions? What is a pseudo-noble gas electron configuration? Problems. How many electrons must each of the atoms below lose to achieve a noble gas electron configuration? Lee. Sr. Al. B.A. Write the symbol of the most common ion formed by each element in problem 6, and name the noble gas with which each ion is isoelectronic. How many electrons must each of the atoms below gain to achieve a noble gas electron configuration? Br. S. N. I. Write the symbol of the most common ion formed by each element in problem 8, and name the noble gas with which each ion is isoelectronic. Write electron configurations for each of the following atoms. Then write the symbol for the most common ion each would form and the electron configuration of that ion. B. Cl. Se. Rb. Write electron configurations for the following ions: Cs+, Y3+, Ni2+, S3, Te2, Ag+, Pb4+, Mn2+. For each ion in problem 11, state whether it has 1. A noble gas configuration, 2. A pseudo-noble gas configuration, or 3. Neither. Split the following ions into isoelectronic groups by noble gas: O2, senior 2+, Ca2+, H, V5+, I, Ba2+, Na+, S2, Al3+, La3+, Li+, S3. 8.2 Ionic bonds and ionic compounds. Lesson objectives. Explain how an ionic bond is formed when electrons are transferred from one atom to another in terms of the resulting electrostatic attraction. Draw diagrams showing this process. Describe the structural arrangements of ions in a crystal, including coordination number and its relationship to a given compound's formula unit. Explain how various physical properties result from the ionic crystal lattice, such as strength, hardness, high melting points, brittleness, and electrical conductivity. Lesson vocabulary. Coordination number. Formula unit. Ionic bond. Ionic compound. Check your understanding. Recalling prior knowledge. What types of charged particles attract each other and what types repel each other? How is an empirical formula different from a molecular formula? What is a crystal lattice? Most of the rocks and minerals that make up the Earth's crust are composed of positive and negative ions held together by ionic bonding. An ionic compound is an electrically neutral compound consisting of positive and negative ions. You are very familiar with some ionic compounds, such as sodium chloride, NaCl. A sodium chloride crystal contains equal numbers of positive sodium ions, Na+, and negative chloride ions, Cl. Ionic bonds. Oppositely charged particles attract each other. This attractive force is often referred to as an electrostatic force. An ionic bond is the electrostatic force that holds ions together in an ionic compound. The strength of an ionic bond is directly dependent upon the magnitudes of the charges and inversely dependent on the distance between the charged particles. For example, a cation with a 2 plus charge will make a stronger ionic bond than a cation with a 1 plus charge. Additionally, a larger ion will form a weaker ionic bond than a smaller ion, due to the larger distance between its nucleus and the electrons of the oppositely charged ion. Watch an animation of ionic bonding at http://www.dlt.ncsm.edu/chapter9-bonding_chapter9-animation/ionic bonding.html. How does this animation represent the transfer of electrons? How do the sodium chloride units join together? Electron dot diagrams. We will use sodium chloride as an example to demonstrate the nature of the ionic bond and how it forms. As you know, sodium is a metal, and it can lose its 1 valence electron to become a cation. Chlorine is a nonmetal, and it gains 1 electron to become an anion. By forming ions in this way, both atoms achieve a noble gas electron configuration. However, electrons cannot be simply lost to nowhere in particular, nor can they be gained without a source. In the case of sodium chloride, a single electron is transferred from the sodium atom to the chlorine atom, as shown below. Figure 1. The ionic bond is the attraction between the Na ion and the Cl ion. It is conventional to show the cation without any dots around the symbol, since the energy level that originally contained the valence electron, S, is now empty. The anion is now shown with a complete octet of electrons. For a compound such as magnesium chloride, the two elements are not combined in a 1:1 ratio. Because magnesium has 2 valence electrons, it needs to lose both to achieve a noble gas configuration. Since chlorine only has room for 1 more electron in its valence level, 2 chlorine atoms must be present as electron acceptors in order to form each Mg2+ ion. Figure 2. The final formula for magnesium chloride is MgCl2. Formula units. The formula unit is the lowest whole number ratio of the ions present in an ionic compound. The formula unit of sodium chloride is NaCl, while the formula unit of magnesium chloride is MgCl2. The formula unit of an ionic compound is always an empirical formula. In a previous chapter, Chemical Nomenclature, you learned how to write correct formula units for ionic compounds by employing the crisscross method. Ionic compounds. The electron dot diagrams show the nature of the electron transfer that takes place between metal and non-metal atoms. However, ionic compounds do not exist as discrete molecules, as the dot diagrams may suggest. In order to minimize the potential energy of the system, as nature prefers, ionic compounds take on the form of an extended 3-dimensional array of alternating cations and anions. This maximizes the attractive forces between the oppositely charged ions. The figure below, shows 2 different ways of representing the ionic crystal lattice. A ball and stick model makes it easier to see how individual ions are oriented with respect to one another. A space-filling diagram is a more accurate representation of how the ions pack together in the crystal. Figure 3. 2 models of a sodium chloride crystal are shown. The purple spheres represent the Na and ions, while the green spheres represent the Cl ions. In an expanded view, the distances between ions are exaggerated, more easily showing the coordination numbers of each ion. In a space-filling model, the electron clouds of the ions are in contact with each other. Coordination number. The coordination number is the number of ions that immediately surround an ion of the opposite charge within a crystal lattice. If you examine the figure above, you will see that there are 6 chloride ions immediately surrounding a single sodium ion, so the coordination number of sodium is 6. Likewise, 6 sodium ions immediately surround each chloride ion, making the coordination number of chloride also equal to 6. Because the formula unit of sodium chloride displays a 1:1 ratio between the ions, the coordination numbers must be the same. The formula unit for cesium chloride is CsCl, also a 1:1 ratio. However, as shown below, figure below, the coordination numbers are not 6, like they are in NaCl. The center Cs end ion is surrounded by 8 Cl ions at the corners of the cube. Each Cl ion is also surrounded by 8 Cs end ions. The coordination numbers in this type of crystal are both 8. CsCl and NaCl do not adopt identical crystal packing arrangements because the Cs end ion is considerably larger than the Na end ion. Figure 4. In a cesium chloride crystal, the cesium ion, orange, occupies the center, while the chloride ions, green, occupy each corner of the cube. The coordination number for both ions is 8. Another type of crystal is illustrated by titanium, 4, oxide, TiO2, which is commonly known as rutile. The rutile crystal is shown below, figure below. Figure 5. Titanium, 4, oxide forms tetragonal crystals. The coordination number of the Ti4+ ions, gray, is 6, while the coordination number of the O2 ions, red, is 3. The gray Ti4+ ions are each surrounded by 6 red O2 ions. The O2 ions are each surrounded by 3 Ti4+ ions. The coordination of the titanium, 4, cation is 6, which is twice the coordination number of the oxide anion, which is 3. This fits with the formula unit of TiO2, since there are twice as many O2 ions as Ti4+ ions. The crystal structure of any ionic compound must reflect its formula unit. For example, in a crystal of iron, 3, chloride, FeCl3, there are 3 times as many chloride ions as iron, 3, ions. View an animated example at http://www.dlt.ncsm.edu/core/chapter9-bonding_and_chapter9-animation/ionic-bonding.html. How does this animation represent the transfer of electrons? How do the sodium chloride units join together? To better understand the structures and properties of ionic compounds, go to http://www.chemguide.co.uk/atoms/structures/ionics-ct.html. Physical properties of ionic compounds. Pictured below, figure below, are a few examples of the color and brilliance of naturally occurring ionic crystals. Figure 6. In nature, the ordered arrangement of ionic solids gives rise to beautiful crystals. A. Amethyst, a form of quartz, SiO2, whose purple color comes from iron ions. B. Cinnabar, the common name for mercury. 2. Sulfide, HGS, which is the primary ore from which mercury is obtained. C. Azurite, a copper-containing mineral, Cu3, CO3, 2, O2. D. Vanadinite, the primary ore from which vanadium is obtained, Pb5, VO4, 3Cl. The regular and orderly arrangement of ions in the crystal lattice is responsible for the various shapes of these crystals, while transition metal ions give rise to the colors. Because of the many simultaneous attractions between cations and anions that occur, ionic crystal lattices are very strong. The process of melting an ionic compound requires the addition of large amounts of energy in order to break all of the ionic bonds in the crystal. For example, sodium chloride has a melting temperature of about 800 degrees Celsius. Ionic compounds are generally hard but brittle. Why? It takes a large amount of mechanical force, such as striking a crystal with a hammer, to force one layer of ions to shift relative to its neighbor. However, when that happens, it brings ions of the same charge next to each other, figure below. The repulsive forces between ions of the same charge causes the crystal to shatter. When an ionic crystal breaks, it tends to do so along smooth planes because of the regular arrangement of the ions. A two-dimensional cross-section of a sodium chloride crystal is shown. B. When struck by a hammer, the negatively charged chloride ions are forced near each other, and the repulsive force causes the crystal to shatter. Another characteristic property of ionic compounds is their electrical conductivity. The figure below, shows 3 experiments in which 2 electrodes that are connected to a light bulb are placed in beakers containing 3 different substances. Figure 8. A. Distilled water does not conduct electricity. B. A solid ionic compound is also not very conductive. C. A solution of an ionic compound dissolved in water conducts electricity well. In the first beaker, distilled water does not conduct a current because water is a molecular compound. In the second beaker, solid sodium chloride also does not conduct a current. Despite being ionic and thus composed of charges particles, the solid crystal lattice does not allow the ions to move between the electrodes. Mobile charged particles are required for the circuit to be complete and the light bulb to light up. In the third beaker, the NaCl has been dissolved into the distilled water. Now the crystal lattice has been broken apart and the individual positive and negative ions can move. Cations move to one electrode, while anions move to the other, allowing electricity to flow, figure below. Melting an ionic compound also frees the ions to conduct a current. Ionic compounds conduct an electric current when melted or dissolved in water. Figure 9. In an ionic solution, the A and ions migrate toward the negative electrode, while the B ions migrate toward the positive electrode. Lesson summary. 1 or more electrons are transferred from a metal atom to a nonmetal atom to form ions. Ionic bonds are the electrostatic attractions between positive and negative ions. An ionic compound is a three-dimensional network of alternating cations and anions that are mutually attracted to one another. The coordination number of an ion is the number of nearest neighbors that it has within the crystal lattice. Ionic compounds are hard and have high melting points. They are difficult to break but are also very brittle. They conduct electricity only when melted or dissolved in water to form a solution. Lesson review questions. Reviewing concepts. Draw an electron dot diagrams for the following atoms and ions. S. S2. CS. CS+. P. P3. SN. SN2+. Which of the following pairs of atoms would be expected to combine chemically to form an ionic compound? Explain. Li and O. N and H. Al and S. Cl and F. Senior and Br. Zn and I. Explain why most ionic compounds are strong and hard, yet brittle. Explain why potassium fluoride does not conduct an electric current as a solid, but it does conduct after being dissolved in water. Problems. Use electron dot diagrams to demonstrate the formation of ionic compounds involving the following elements. Use arrows to show the transfer of electron, S, from one atom to another. K and O. Ca and N. Ba and S. Write the formula units for each of the ionic compounds from question number 5. Answer the following. What is a coordination number? If the coordination numbers for each of the two ions in a crystal lattice are identical, what must be true about the formula unit of the compound? An ionic compound forms between metal A and nonmetal B. The coordination number of the cation of element A is 4 and the coordination number of the anion of element B is 8. Write the chemical formula of the compound. A general ionic bond forms between a cation X and an anion Y. How will the strength of the ionic bond change if the following changes are made? In other words, will the resulting bond be stronger or weaker? The charge of the cation is doubled. The size of the cation is increased. 8.3 Metallic bonds. Lesson objectives. Describe the electron C model of metallic bonding. Explain how metallic bonding is responsible for the conductivity and luster of metals. Explain why metals are malleable and ductile, while crystalline ionic compounds are not. Describe how metal atoms are arranged, including the 3 most common packing systems. Identify some common alloys and explain their importance. Lesson vocabulary. Alloy. Closest packing. Metallic bond. Check your understanding. Recalling prior knowledge. How are the cations and anions in an ionic crystal arranged? What happens to an ionic crystal when it is put under a large stress? The bonding that occurs in a metal is responsible for its distinctive properties, including luster, malleability, ductility, and excellent conductivity. The metallic bond. Pure metals are crystalline solids, but unlike ionic compounds, every point in the crystal lattice is occupied by an identical atom. The electrons in the outer energy levels of a metal are mobile and capable of drifting from one metal atom to another. This means that the metal is more properly viewed as an array of positive ions surrounded by a sea of mobile valence electrons. Electrons which are capable of moving freely throughout the empty orbitals of the metallic crystal are called delocalized electrons, figure below. A metallic bond is the attraction of the stationary metal cations to the surrounding mobile electrons. Figure 1. In a metal, the stationary metal cations are surrounded by a sea of mobile valence electrons that are not associated with any one cation. Properties of metals. The metallic bonding model explains the physical properties of metals. Metals conduct electricity and heat very well because of their free-flowing electrons. As electrons enter one end of a piece of metal, an equal number of electrons flow outward from the other end. When light is shown onto the surface of a metal, its electrons absorb small amounts of energy and become excited into one of its many empty orbitals. The electrons immediately fall back down to lower energy levels and emit light. This process is responsible for the high luster of metals, figure below. Figure 2. The American Platinum Eagle is the official platinum bullion coin of the United States and was first minted in 1997. The luster of a metal is due to its metallic bonds. Recall that ionic compounds are very brittle. Application of a force results in like-charged ions in the crystal coming too close to one another, causing the crystal to shatter. When a force is applied to a metal, the free-flowing electrons can slip in between the stationary cations and prevent them from coming in contact. Imagine ball bearings that have been coated with oil sliding past one another. As a result, metals are very malleable and ductile. They can be hammered into shapes, rolled into thin sheets, or pulled into thin wires. Watch a demonstration of metallic bonds in pewter balls when dipped in liquid nitrogen at http://education.jlab.org/frost/pewter_bells.html. Crystal structures of metals. If you wanted to make a stack of identical spheres, you might come up with an arrangement like the one shown below, figure below. Figure 3. When identical spheres are stacked, each successive layer fits into the small spaces where different spheres come together. Closest packing minimizes the amount of empty space and is how metal atoms are arranged in a crystal. This orderly and regular arrangement of the metal balls minimizes the empty space between them. Closest packing is the most efficient way to pack spherical objects. The atoms in a metal crystal are arranged in similar patterns, called close-packed structures. Pure metals adopt one of several related close-packed structures, as pictured below, figure below. Figure 4. Most pure metals naturally adopt one of these three closest packing arrangements. On the far left is the body-centered cubic, BCC, structure. In that crystal, metal atoms occupy the 8 corners of a cube along with one atom in the very center. The coordination number of each atom in the body-centered cubic structure is 8. In the face-centered cubic, FCC, structure, there are 8 atoms at each corner of the cube and 6 atoms in the center of each face. The coordination number of each atom in the face-centered cubic structure is 12. The atoms in a hexagonal close-packed, HCP, structure also have a coordination number of 12, but crystals of this type are hexagonally shaped rather than cubic. Alloys. An alloy is a mixture composed of 2 or more elements, at least one of which is a metal. You are probably familiar with some alloys such as brass and bronze, figure below. Brass is an alloy of copper and zinc. Bronze is an alloy of copper and tin. Alloys are commonly used in manufactured items because the properties of these metal mixtures are different, and sometimes more useful, than those of a pure metal. For example, bronze is harder than copper and more easily cast. Brass is very malleable, and its acoustic properties make it useful for musical instruments. Figure 5. Bronze, an alloy of copper and tin, has been in use since ancient times. The Bronze Age saw the increased use of metals rather than stone for weapons, tools, and decorative objects. Brass, an alloy of copper and zinc, is widely used in musical instruments like the trumpet and trombone. Steels are a very important class of alloys. The many types of steels are primarily composed of iron, with various amounts of the elements carbon, chromium, manganese, nickel, molybdenum, and boron. Steels are widely used in building construction because of their strength, hardness, and resistance to corrosion. Most large modern structures like skyscrapers and stadiums are supported by a steel skeleton, figure below. Figure 6. The Willis Tower, formerly called the Sears Tower, in Chicago was once the tallest building in the world and is still one of the tallest in the Western Hemisphere. The use of steel columns makes it possible to build taller, stronger, and lighter buildings. Alloys can be one of two general types. In one type, called a substitutional alloy, the various atoms simply replace each other in the crystal structure. In another type, called an interstitial alloy, smaller atoms such as carbon fit in between the larger atoms in the crystal packing arrangement. Lesson summary. A metallic bond involves the attraction of stationary metal cations to a surrounding sea of mobile valence electrons. Metallic bonding directly contributes to properties such as high electrical and thermal conductivity, malleability, ductility, and luster. Metal atoms are arranged in regular, orderly patterns that often correspond to various closest packing arrangements for spheres. Alloys are mixtures of metals. Many alloys are widely used because their properties are often more useful for certain applications than those of pure metals. Lesson review questions. Reviewing concepts. Which of the following elements displays metallic bonding? Se. Ti. Ru. Te. Explain the behavior of electrons in a metal. How does a metallic bond contribute to the electrical conductivity of metals? Name the three common closest packing arrangements of metal atoms in a crystal. Give an example of a metallic element that crystallizes in each form. Problems. Why are ionic crystals brittle, while most metals are malleable? What are some advantages of using steel rather than iron? Sodium has 1 valence electron per atom, while magnesium has 2. Predict whether sodium or magnesium has stronger metallic bonds. How do you think that you could test your hypothesis? What are the coordination numbers of a metal atom in a body-centered cubic structure and in a face-centered cubic structure? In which type are the atoms more closely packed? Iridium is one of the densest known elements at 22.6 G/cm3. In which crystal structure do you think iridium is more likely to crystallize?